Hey guys, welcome back to my channel. So in this video, we're going to talk about the other two situations where resonance can happen. If you haven't checked out my video where I talked about the first two situations where resonance can happen, please go back and check it out. Now we're going to jump right into the third example, okay? So the third example is when I have a double bond. So my double bond is here. That is next to a negatively charged carbon, which is here, right? Okay, perfect. So whenever you see a negatively charged carbon, I would like you to realize I always have 3 bonds and one set of lone pair of that carbon when the carbon is negative, because that would give me formal charge of 4. I have 3 bonds plus 2 electrons, which is -1. So that's what gives this carbon the negative charge here, okay? Perfect. So now, since we have a set of a lone pair here of this carbon, this set of lone pair is just as anti as the other lone pairs, the lone pairs of oxygen, the lone pair of nitrogen. So it would move itself to the adjacent spot towards the double bond here, okay? So let's draw the structure after the movement of the set of lone pair and see what happens. Okay, so now I have moved my lone pair. So I deleted, I got rid of my lone pair, and then I draw a double bond here, right? Since I moved my lone pair to create this double bond. So I still have my hydrogen here, right? That doesn't change. Okay, so which means this carbon now have 1, 2, 3, 4 bonds, which is perfectly neutral, right? 4 minus 4 equals 0. So I don't need this negative sign anymore, right? Since I have a neutral carbon here, okay? So, but the problem we created is this carbon. If you look at this carbon, you will see 1, 2, 3, 4, 5 bonds here, right? Which violates the octet rule, right? Which is no good. Okay, so how can we solve the problem? So the truth is, when let's go back to our original structure. So when we have this lone pair move the electrons to this spot, creating a double bond, simultaneously this bond here will be broken to give the 2 electrons to this oxygen, which adds an extra set of lone pair to the oxygen, okay? Okay, so now let me break this bond by assigning an extra set of lone pair to oxygen, right? Originally, oxygen had 2 sets of lone pair. I still have my 2 sets of lone pair here. It's just that this extra set of lone pair is from this double bond that I just broke, right? Okay, perfect. Alrighty. So now let's see if my carbon is okay now. My carbon is okay now because I have 1, 2, 3, 4 bonds, which gives this carbon 0 formal charge, a neutral carbon. But my oxygen has a different charge now, right? My oxygen has 6 plus I have 1 bond and 6 electrons. So that gives me -1 negative charge of this oxygen, okay? Perfect. Let me clean it up for you. So this will be the structure that I draw for this problem. This will be the resonance structure that I draw for this problem, okay? And then really quickly, if your professor asks you on the exam, which structure, if it's this one or that one, that is more stable, you would pick this one, right? Why? Because oxygen here is better off with its negative charge than this carbon having the negative charge, right? Because oxygen has a higher value of electronegativity than carbon, which means oxygen is more electronegative than carbon. It likes electron-negative stuff more than a carbon does. So this structure will be more stable than the other one. Okay, now let's draw the hybrid structure, okay? Okay, now let's draw the hybrid structure. Okay, so to draw the hybrid structure, let me use a different color to track the distribution of my charges, okay, and also the distribution of my double bonds. Okay, first, my carbon here, I'm so sorry, I meant to use this. So my carbon here had a negative charge first, and then the negative charge went to oxygen, okay? And then first, I had my double bond here, and then I ended up having my double bond here, right? Okay, so if I were to draw my hybrid structure, I would draw something like that, okay? And then I will assign the partial negative charge to my carbon and my oxygen, okay? So just like I said in my first video, in the part 1 video, resonance is really an ongoing process where nor this oxygen spot, neither this oxygen nor this carbon spot that has absolutely negative charge, okay? It's an ongoing process. So as soon as, like here, as soon as we give the oxygen its negativity, the structure will resonate right back to the status where the carbon has a negative charge, right? So it's really an ongoing process. That's why we use this two-way arrow instead of a one-way arrow, because it's not that we're drawing some product of a chemical reaction that goes one way. It's an ongoing structure that gives my atoms partial negative charges, right? Okay, and then also the dashed line of the double bond here indicates this ongoing process of forming the double bond, okay? Perfect. So that's all about this example, okay? Let's move on to the next one. So this is the last situation I want to discuss where the resonance can happen. And this is actually a fairly complicated example, but it's okay. I think at this point, I believe you guys, you really get this. So let's go over this, okay? So when I have a double bond, so I have a double bond here, and double bond here, okay? So you may be asking, okay, which double bond are you talking about? So let's see what is next to this double bond. So I'm talking about the double bond that is next to an atom with a lone pair, okay? So looking at all my atoms here, nitrogen is the only atom that has a set of lone pair, right? So very obviously, the double bond that I'm talking about is the double bond that is highlighted in yellow, right? Okay, perfect. So how the resonance happens is the movement of this set of lone pair of nitrogen would initiate the process of resonance, okay? So the set of lone pair would move the 2 electrons to form a new bond at this adjacent spot towards the double bond. So this lone pair will form a double bond here, a new bond here. So let's draw the structure after the formation of this extra bond here, okay? Okay, let me just copy and paste it. No. Okay, perfect. So now let me get rid of this lone pair and then create a extra bond here, okay? So this creates a problem, okay? So you may be saying, okay, do you mean the problem of this nitrogen has a different charge now? True, okay, nitrogen does have a different charge now, because before nitrogen had a 3 bonds plus 2 electrons, so nitrogen has a perfectly zero formal charge, which gives it gives it no charge, right? It's neutral. But now our nitrogen has 4 bonds around it, right? The double bond, the set of lone pair is gone, right? So I only have 4 bonds here, so which gives me a positive charge of this nitrogen, okay? But that's not the end of the world. That's fine, since nitrogen still has 8 valence electrons. So as soon as the octet rule is not violated, nitrogen is okay, okay? The problem is this carbon here, now it has 1, 2, 3, 4, 5 bonds here. This creates 10 valence electrons of this carbon, and it's a violation of octet rule, right? We always want 8 valence electrons of our atom to fulfill the octet rule. So this is a problem that we need to solve, okay? How is that problem solved? So what actually happens is, when this set of lone pair of nitrogen, when it creates this double bond, simultaneously, this double bond here will be broken, right? How was it broken? You cannot just say, oh, I want to break it, and it's magically broken. No, you got to assign the 2 electrons of that double bond to somewhere else to break that double bond, right? Okay, so in this case, it's this carbon that accepts the 2 electrons of that soon to be broken double bond, right? Okay, perfect. So now let me assign the electrons. Let me get rid of the double bond. I broke this double bond. I assign the electrons to this carbon. Okay, what does that do to this carbon now? This carbon is fine now because it has 1, 2, 3, 4, bonds, right? It doesn't have 5 bonds anymore. No more 10 valence electrons, 8 electrons around this valence electrons of this carbon, so it's fine. But this carbon has a different charge now, right? Since it originally has 1, 2, 3, 4 bonds, right? Now my hydrogen is still here. It was never lost. So that gives my carbon a negative charge here. If you were to calculate the formal charge, you have a 4 minus, I have 3 bonds plus 2 electrons. That gives me -1. Right? That's how the negative charge is from here, okay? So my carbon here has a negative charge now, okay? So let's see the structure, okay? Let's take a close look at this structure. Is this the end of my resonance structure, right? Does the resonance keeps going? Actually, it does. Why? Since I have a negative charged carbon here next to a double bond, right? Still remember the third example that we discussed when we have a negatively charged carbon next to a double bond, the lone pair of the double carbon would move itself to create a new bond, and at the same time we break another bond, right, to fulfill the octet rule. That's what this example is about. Okay, so same thing happens here. Okay, so this set of lone pair would have moved the electrons here to create a new bond. And at the same time, this bond will be broken, assigning the 2 electrons to this carbon. Okay, so now let's draw the structure after this. Okay. Okay, perfect. So my positive nitrogen is still here, connected to hydrogen and CH3. Okay, but my lone pair of this carbon is not here anymore since I create a double bond here, right? I create a bond here. And then I also assign the 2 electrons of this original double bond here. Now I got rid of it, okay? By assigning the electrons here to this carbon, okay? That would give my carbon here a negative charge, right? Okay, and then this guy, this double bond, he never did one single thing. So he is still here, right? Okay, perfect. Now, what happens? Do you still see a negatively charged carbon next to a double bond? Oh yeah, yes you do, right? So the resonance structure will keep going, okay? So let's keep drawing the structure. So the movement is this set of lone pair moves the electrons to this spot, and then this double bond will be broken by assigning the electrons to this carbon, okay? Okay, perfect. So I still have my nitrogen here, okay? And then this guy didn't do anything this time. It was this lone pairs, right? It was this set of lone pair that creates this new double bond. And I broke this double bond here by assigning the 2 electrons to this carbon here, right? Which gives my carbon a negative charge, okay? So now you can still see I have a negatively charged carbon that is next to a double bond, right? So I can really keep drawing my resonance structure, okay? So let's keep drawing the resonance structure, okay? Let's do the arrow first, okay? My lone pair would create a new bond here, and then one of these bonds would be broken by assigning the 2 electrons to my adjacent atom, which is the nitrogen here, right? Okay, so now let's draw the structure. Okay, so I still have this guy here and this guy here, okay? So my lone pair here is moved to here, right? Okay, and then I had 2 bonds here, but now this bond is broken by assigning the lone pair to the nitrogen, right? Okay, so my nitrogen is still attached to my hydrogen and my CH3, okay? So that gives nitrogen a neutral charge again, right? I don't need that positive charge of nitrogen anymore, right? This is my this is the end of my resonance structure, okay? And then this structure and this structure goes back and forth, right? If you take a look at this benzene ring here, which has a let me delete things here. Okay, so if you look at this benzene ring, it is a ring like that, right? So this benzene ring would have formed a structure like that. It keeps going. This happens simultaneously, right? This happens all the time. That's why sometimes we also see a structure like that. Okay, these are all equivalent, right? Okay, perfect. So this is the resonance structure of this problem. Okay, so to really finish this problem, I have to draw how many structures? I have to draw 1, 2, 3, 4. Okay, I have to draw these 4 structures to complete this resonance structure problem. Okay, and then now let's draw the hybrid structure. Okay, so to draw the hybrid structure, this is pretty actually challenging. So let's use 2 different colors to trace the distribution of my double bond and my charges. Okay, so first I had my double bonds here, right? Okay, and then I created a double bond here. Okay, and then I created a double bond here, right? Okay, and then I created a double bond here, and lastly I created a double bond here. Okay, perfect. Now let's use a different color to track the charges. Okay, so first my nitrogen had again a positive charge, right? And then it was this carbon that had a negative charge. Okay, and then it was this carbon. Okay, and then it was this carbon. Okay, so now I'm ready to draw my hybrid structure. Okay, so let me first draw the double bonds. Okay, so first of all, I had my double bonds here, here, and here, right? That's my original structure, my original status. Okay, and then I created a bond here, okay, right? Which is here, okay? And then I created a double bond where? Here, right? Okay, so I have my double bond created here, and then my double bond moves here, so I have this double bond, right? Okay, and lastly, I had a double bond here, so let me connect this. Okay, perfect. Okay, now let me assign the charges to my atoms. Okay, so nitrogen is actually partial positive, and then I had 3 carbon spots where I had negative charges, but they're really just partial negative charges, right? So first it was this carbon that had a negative charge, so partial negative here, and then it was this carbon, partial negative here, and lastly it was this carbon, partial negative here, right? Okay, this is the hybrid structure for this problem. Okay, this is pretty complicated. It takes a lot of practice to get comfortable, so just practice a lot, draw this a lot in your sleep, in your dream, you know, and then eventually you will feel this, you will feel comfortable with this. Okay, it makes so much sense. Okay, alrighty, and then before we end this video, I just want to ask you guys a really quick question. Okay, so if you notice this structure here, okay, this is just what we did just now, right? Okay, so this is just this structure we have here, right? Exactly the same thing. Okay, I just added another substituents here. Okay, so my question is, do you think the lone pairs of this oxygen would initiate resonance structures as this lone pair of nitrogen did? Think about this. Okay, the answer is no. Okay, why? Because the lone pair of this nitrogen is right next to my double bond. Okay, if you see here, number 4, if you take a look at what I put here, when a double bond is right next to an atom with lone pair, which is the case of this nitrogen. But this oxygen and then this double bond, they're like 1 carbon away. There's a carbon in between them, right? So when I move the lone pair of this nitrogen to create a double bond here, I can break this bond, right? I can assign the electrons to this carbon to fulfill the octet rule of this carbon. Whereas imagine if I were to move this set of lone pair of the oxygen here, then I have an extra bond here, right? I have an extra bond here, and then let me delete the lone pair of the oxygen, and then I never lost my hydrogens here, okay? So that would create a problem of this carbon having what? Having 10 valence electrons, right? Which violates the octet rule, 5 bonds, 10 valence electrons. This is no good, okay? Because we don't have a double bond here next to this oxygen that can be broken, right? That can be broken. Yeah, if I had a double bond here, then this double bond can be broken. It can assign its charge to somewhere else. Then it would not violate the octet rule of this carbon, right? But in this case, this cannot happen. Okay, this cannot happen. So let me put the set of lone pair back to my oxygen. So if your professor asks you to circle the lone pairs of this structure that would initiate resonance structure, you would only circle this set of lone pair here, but not these lone pairs. Okay, perfect. So that's all about this video. It's a little bit long. I hope I made things clear. If you like my video, please support me by hitting the like button or subscribe to my channel or comment down below and let me know what you think. Best wishes to your studies. Always ask a lot of questions and stay strong. See you soon. Bye.